All right, so we're going to look at the Calculus 3, third exam, spring 2024. We have 6 problems of fun waiting for us to discover and to solve. Let's get going. Number 1, consider the double integral. 0 to 1, y to 1, e to the x squared dx dy. Now you look at e to the x squared dx and you're like, because you don't want to integrate that. That's terrible. But we're probably not going to quite do that. What are we going to do? Sketch the region of integration, reverse the order of integration, and then evaluate the integral. Okay, so this problem is going to be a little sketchy, right? Okay, now how do we get the region? Well, that is being stored in the bounds. And so we say, okay, hey, there's information to be had here. So we look at our bounds. The outer layer tells us about y, and it says that we're going from 0 up to 1 for y. The inner layer is telling us about x, and it says we're going from y up to 1. All right, so if we want to sketch, well, we are going to have a few pieces. We know that y is going from 0 to 1, so we'll mark 1 here. And then for any choice between 0 and 1, we're going to have x goes from x equals y, that's right, y equals x, x equals y, so that's this line, over to the line x equals 1. So we're going across this way. So this is how we are currently setting up. So this is our region. All right, so that's our region. And just to be abundantly clear, I, of course, as always, bring highlight markers. Why not? It really helps highlight what's going on. Okay, so we've got our region, so we finished the first part. Check. Now, reverse the order of integration. So we're going to change it. Well, that means instead of dx dy, we're going to do dy dx. Okay, so we're doing integral. Function doesn't change. The order changes, dy dx. And now we start saying, okay, well, what happens? Well, where does x go from? Well, x goes from 0. Largest x value is 1. 0, 1. All right, where does y go from? Well, for any particular x value, where do we start? Well, we start at the axis, which is 0, and go up to this line, y equals x. So we're going to up to y equals x. All right, so now we've done it. And then we evaluate. Now, previously it was like, what? E to the x squared? Hopeless. It'll never happen. But now we're like, okay. Because we're integrating not with respect to x, we're integrating with respect to y. So e to the x squared is a constant. So I was like, yeah, no worries. So this becomes integral 0 to 1 of e to the x squared y. Evaluate from y equals 0 to y equals x dx. Well, plug in 0, you get 0. Plug in x, you get x. So this becomes integral 0 to 1 of e to the x squared x dx. Now that looks like an integral we have a hope for because there's an x there. And in particular, we'll try some substitution. So, all right, let's let u equal x squared. And let's see, u equals x squared, du equals 2x dx. We'll go ahead and move that 2 to the other side. And all right, so what would this be? Now, currently, these are x bounds. X equals 0 to x equals 1. But we're doing substitutions. We're going to u bounds. So we're not going from x equals 0 to x 1. We're no longer going from 0 to 1. We're going from 0 to 1. Okay, good. Right? 0 squared is 0. 1 squared is 1. Very dramatic. Okay. E to the u. And then this x dx becomes a 1/2 du. All right. Well, that's 1/2 e to the u. Evaluate from 0 to 1. Which, if you plug in, that's 1/2 e to the 1 is e. And then e to the 0 is 1. So 1/2 times e minus 1. There we go. Lovely answer. One problem done. Number 2. Show that the following vector field is conservative by finding a potential function for it. Okay, so we have 2xy minus z cubed, x squared plus 2yz squared, 2y squared z minus 3xz squared. Now, when we think about this, we say, look, what do we really have? We have an f sub x, an f sub y, and an f sub z. So we know it's conservative. So that says it's the gradient. So in other words, there's some gradient f equal to this bold f. And so our goal is to say, hey, if we have all these partial derivatives, can we reconstruct a function? Now, I really appreciate their choice of the word here, a potential function, because technically there are infinitely many potential functions, but they differ by plus c. So essentially up to a constant, and we don't really worry about constants at this stage. All right, well, how are we going to do it? We're going to integrate, take antiderivatives. And in particular, we say, well, hey, let's look at the following. We're going to look at the integral of f sub x with respect to x. So we're going to integrate 2xy minus z cubed dx. And if we do that, we're going to get integral with respect to x. So y and z's are constants. So that would be x squared y minus, and here, x z cubed plus anything which only depends on y and z. So anything which is constant with respect to x. Now, that's one integral. We'll do two more. We'll then integrate the derivative with respect to y with respect to y. So we're integrating x squared plus 2y z squared with respect to y. Well, x and z are constants, so this is a constant. So you get x squared y. 2y, integral that, is y squared, and z squared is a constant, plus, of course, some function that depends only on x and z. And, all right, the last piece that we need to do is we have the derivative with respect to z. We're going to integrate that with respect to z. So we have integral of 2y squared z minus 3xz squared dz equals, well, now with respect to z, y's and x's are constants. So here it's y squared is the constant, and then we'll get z squared. And then here, x is a constant, and so 3z squared, integrate that, we get z cubed. And plus some function which depends only on x and y. All right. So here's the thing. As we look at it, these are all proper ways to write f. The problem is each one of them has sort of a blinders on. It's like I can't see everything. But by putting it all together, we can capture all the information that's there. So we say, okay, what are we going to have? Well, we're going to look at overlaps. Now, we know it's conservative, but let's pretend we didn't know that. And when we are testing conservative, we'd still get to the same point, but then we check for overlaps and say, do they agree? Well, x squared y, good. And so that tells us that our function f has an x squared y. These agree, and then whatever they agree on, that's in our potential. Now what else? Well, we have a minus xz cubed and a minus xz cubed. So that agrees, and then that's going to be in our function. And then we say, okay, well, what else? Okay, is there anything else? I'm running out of colors. Okay, what about y squared, z squared? Yes, those agree. And so that's in our potential, and we've accounted for everything. And everything's consistent. So when I say consistent here, I mean anything with multiple variables shows up in the right places. So if it involves both x and z, it shows up both in x and in z. So that's what we mean by consistency. So here is our potential function. We found it. There we go. All right, part B. Find all possible values of the constant a so that the integral 211 to a12 of this equals 21. Now, notice, what does this mean? Well, it means that we're in three-dimensional space, and we're going from a point 211, and we're ending at another point, A1, 2. And these are probably not in the right place, but there's a sort of implicit implied we're going from here to there. So it's like there's a curve. But what don't we have? We don't have the curve. What does that tell us? It probably means it doesn't depend on the curve. It's like, oh. And in fact, if we look, it's not a coincidence that this problem is part B and this is part A. Look at the pieces. 2xy minus z cubed. X squared plus 2yz squared. 2x squared z minus 3xz squared. So we're like, hey, fundamental theorem of line integrals. This is equal to, on this side, so 21 is equal to, we can find the potential function, x squared y minus xz cubed plus y squared z squared, and then we evaluate start and stop. So we're going to plug in where we stop, subtract, plug in where we start. All right, so we plug in. So let's see. Everywhere where we see an x, we're going to put an a. So we have a squared, y is 1, minus a times 8. And then y squared is 1 squared, and z squared, 4. All right, that's plug in the end point, subtract, plug in the start point, which is at 2, 1, 1. Okay, so we get 2 squared times 1, 2 times 2 squared, 4. 2 times 1 cubed, minus 2, and 1 and 1, and so 1, 1. All right, so it doesn't hurt to double check. Okay, wherever we saw x's here, you put a's, and y's are 1s, and z's are 2s, and yep, okay, except this should be not a times, should be a plus. Check yourself. As the great philosophers have said, you should check yourself before you make a mistake and look silly. All right. Well, that's not quite what they say, but good enough. Okay. Well, let's see if we can't clean any of this up. All right. Now we have an a squared minus 8a. And then here we have a 4 minus a 4. Oh, well, that's convenient. It's almost like it was meant to work out. Here we have minus 2 plus 1, which makes minus 1, but then it's minus that, so it's really plus 1. But there's this 21 over here, so we have a plus 1. We're going to bring the 21 across, and so that's going to make a minus 20 equals 0. Okay, so cleaning that up, a squared minus 8a minus 20 equals 0. Oh, we're getting close now. What do we have? Quadratic. And if we've lived a good, clean algebra life, and if our professors love us, and I believe in them, they seem like such nice people. They feel like the kind of people who care about their students. This will factor. All right, does it? Do we have two things that multiply to 20, negative 20, but add to negative 8? I think we do. Let's try this. How about 10 and 2? And let's see, minus 10 and plus 2. Does that work? A squared plus 2a minus 10a is minus 8a, and then minus 20. So that leaves us to the conclusion a equals 10 or negative 2. So it turns out for all possible values, there were two of them. And there they are, 10 and negative 2. Woohoo! Nice, fun. And of course, the main thing here, fundamental theorem of line integrals. Look for those conservative functions, then you don't need to worry about endpoints. Whoa, man, that's good. But more problems to do. So on to number 3. Using Green's theorem. You know, I have a hunch that this problem is going to have us use Green's theorem. Don't know what it is, but I just feel it in my bones. Evaluate the line integral, the integral around the closed curve C, tangent of x cubed minus x squared y dx plus y to the fifth plus x squared dy, where C is the path shown in the figure below, consisting of two line segments, so that line segment, this line segment, and a portion of the circle x squared plus y squared equals 1. All right, nice. Now, before we go any further, I do want to say there are hints that we would use Green's theorem even if it didn't explicitly state it. Huge hint number one, this notation. You see that little circle? That means we're doing a integral on a closed curve. Integrals on closed curves is a big flag that says Green's theorem. All right, so if you see integral on closed curve, think Green's theorem. And what else do we notice? Well, we notice that there's some pretty unpleasant, you might even call them unsavory pieces of our function. Tangent of x cubed, we're expected to integrate that? That's hopeless, hopeless. So we want to get rid of it. And that's where the theory comes into play. So the nice thing about Green's theorem is some things that look hopeless will go away. All right, so let's think about what's going on. Now, we're going to mark a few things. And first off, we have this nice closed curve. I'm going to make it a little bit bigger just to help highlight it. And okay. And it encloses a region R. So here's our closed curve C. It encloses a region R, which is a quarter circle. And all right, so now, what does Green's theorem say? Well, it says the following. It says if we are integrating on a closed curve around C, which is the boundary of our region, m dx plus n dy, and if orientation is correct, which means that as we move around the curve, some people like to say counterclockwise, but I think it's a little bit more specific. I remember the song, to the left, when you walk the curve, keep the region to your left. Right? So, no, to the left. So walk along the curve, we're walking along the curve, we're walking. We want to make sure that our region is to the left-hand side of ourselves. Okay, so that's the orientation, which is good. We've got the right orientation. And so having the right orientation, if we didn't, well, we can fix it. It just changes a sign. All right, so pay attention. So that's equal to the integral over your region, n sub x minus m sub y. All right, now, all of this is to say that for us, the integral over our curve, we are really asking the integral over our region of, take the derivative of this term with respect to x. Y is a constant when we take the derivative with respect to x, so we're getting y squared minus. Now here, we're going to take m sub y. X is a constant, so the tangent x cubed goes away. So like we anticipate, something should make this go away. And take the derivative with respect to y, we get minus x squared and dA. So, okay, so really we're integrating over this region of, we could say x squared plus y squared. And we look at it and say, whoa, x squared plus y squared. Hey, that's cool, because what's going on? This x squared plus y squared, combined with being pieces of a circle, that's telling us polar. So we're going to get to do a polar integral. All right, so quick reminders, if you ever need them. X equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared. And, okay, so for us, we're in polar, so integral, x squared plus y squared becomes r squared, dA is r dr d theta. Now, where does theta go from? Well, we're starting at 0, and then we're spinning, and we stop at pi over 2. It's not a full circle, it's only a quarter circle. So 0 to pi over 2. Where does r go from? Well, r is relate to the origin. So we go from the origin, and we move out till we hit the circle. So from the origin to the unit circle, 0 to 1. All right, well, r squared times r is r cubed. Integral of r cubed is 1/4. fourth r to the fourth. Evaluate from 0 to 1. Well, okay, so that becomes 1/4. So we're integrating 0 to pi halves of 1/4. That's 1/4 theta from 0 to pi halves, which plug in 0, you get 0, plug in pi halves, so you get 1/4 times pi halves, also known as pi over 8. Ah, nice, nice. See, we didn't have to worry about that tangent x cubed. As predicted, if you know the theory, things are nice. And in particular, if things look impossible, it probably is a sign. It's impossible. Be smart. Don't start. All right, that's number 3. Number 4. Write the integral -2 to 2. Negative root 4 minus x squared, 2 root 4 minus x squared, 0 to root 4 minus x squared minus y squared, z, dz, dy, dx in spherical form. So spherical form means spherical coordinates. So we need to sort of do some quick refreshers of what's going on here. But first off, before we get to spherical coordinates, what's our region? So we can combine things, right? We know where x goes, we know where y goes, we know where z goes. So x is going from -2 to 2, and then y goes from negative root 4 minus x squared, less than equal to y, less than equal to root 4 minus x squared. Now, if we think about that in the plane, so -2 to +2, what are these curves? Y equals plus or minus 4 root x minus y squared. Well, in both cases, what you can do is you can square both sides. You get y squared equals 4 minus x squared, or x squared plus y squared equals 4. So it's like, that's like a circle, isn't it? It is a circle. It's a circle of radius 2. So it's like, okay, so this is a circle of radius 2. So this is our region in the xy plane. All right, now, z equals 0 is the xy plane. So we're going from the xy plane up to something. So the last piece of our puzzle, what is this z equals square root 4 minus x squared minus y squared? Square both sides, and you get z squared equals 4 minus x squared minus y squared. And you're like, wait a second, that looks like x squared plus y squared plus z squared equals 4. That's the sphere of radius 2. Well, wait, I have a circle of radius 2, and I'm going from that circle up to a sphere of radius 2. Okay, I think I know what this looks like then. So this is just a very fun and maybe overly complicated, but really it's because we're in our coordinate system here. We have a half a sphere. So here's our region down in the plane, and then we're going up to our sphere. Okay, so it's half a sphere. So half a sphere of radius 2. All right, now, next up, we need to think about changing things into spherical coordinates. All right, so we've got lots of bits and pieces here. I feel like I could spend an hour talking about this problem, but there's other problems. We can't spend the whole time here, no matter how much fun we have. All right, so let's do a quick summary. Let's remind ourselves of a few things. First off, we have some nice things. We have theta, phi, rho. So theta is really about spinning around the z-axis, like how far do you spin around the z-axis. Phi is about how far off you come from the z-axis, and rho is how far out you go from the origin. Now, when it comes to changing from Cartesian into sphericals, the 3 most important things to remember are that x squared plus y squared plus z squared equals rho squared, that rho cosine phi equals z, and rho sine phi is r, the same kind of r that you see in polar coordinates. Okay, so we have that in our back pockets. Now, that's about polar coordinates. the last little piece that we need is to remember about changing volumes. Because every time we change coordinate systems, it's really, we have to make sure we take care of three things in our integrals. Because every integral has three things. The function, which we'll get to, the bounds, which we'll get to, and how you break things up. That's our Jacobian part. And so here's the thing to remember. Right now we have dz, dy, dx. That's essentially our piece of volume. So what does that become in spherical? Remember the song. Rho, rho, sine of phi, d rho, d phi, d theta. Yes, don't forget it. All right, so here we go, and we're almost there. So we're going to have our integral, integral, integral. So let's deal with our function, z. Well, good news, we know what our function is going to become, rho cosine phi. So there's our z. The dz, dy, dx becomes rho, rho sine of phi. You're probably like, can you do that without singing the song? No, 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 I can't. I need to sing the song. All right, theta, bounds. Now here, we can look at our picture. Like theta is how much we spin. And we see it's fully symmetrical. So we're doing the full revolution. 0 to 2 pi. Now, phi. Phi we think about. So we start by saying, okay, where are we hitting our region? Well, if we're going straight up, yes, we're hitting our sphere. And we're hitting our sphere, we're hitting our sphere, we're hitting our sphere until we are at 90 degrees. When we've hit 90 degrees, that means we've hit the xy plane. Now, once we go below 90, we're going to places below the xy plane. None of our region is there. So our bounds for phi are 0 to pi over 2. All right, then our last one, rho. Well, we're going out from the origin. So it acts like r does in polar. We say, how does everything tie back to the origin? So we have 0, the origin, and we move out until we hit the sphere. And the sphere has distance 2. And it's distance 2 regardless of our choice of theta, regardless of our choice of rho between 0 and pi halves. We always have to go out distance 2 to that sphere. That's why spherical coordinates are called spherical coordinates, because they work really nicely with spheres. Coincidence? I think not. Are we done with part A? Yeah, actually we are. That is part A. Oh, good, good, good. Now, part B. Evaluate the integral in A. So now evaluate this integral, but use this version of it. Why? Because it has a lot less square roots. So it's probably a little bit easier to do. We probably could have actually done this, looking up. We could have done it either way, but we're going to do it here. Now, what's nice about this integral versus this integral? Look at your bounds. What do you notice about these bounds? They're all numbers, right? There's no place where there's a function here. Now, what does that tell you? Well, it tells you can really just pull this apart into 3 integrals, assuming, of course, that your functions you can pull apart into multiplying of 3 pieces. So if you think about your function, what do we have? Well, we really have rho cubed, and then we have cosine phi sine phi. And okay, great. And then we also have, floating in the background, 1. So we say, okay, so this is our part of rho. Here's our part with phi. And then here's our part with theta. So this integral, pulling it into pieces, 0 to 2 pi d theta. The second part, 0 to pi halves. Cosine phi sine phi d phi. And then the last part, rho integral 0 to 2, rho cubed d rho. Okay, all right, well, we're close, and we just have to work through these integrals one by one. All right, well, which one first? Let's try this one. That's looking pretty happy. That's theta. Evaluate from 0 to 2 pi, which is 2 pi. Nice. Now this one we can do it in a couple of different ways. We could do some substitution. We can do some trig identities. Let's do some substitution. Suppose you let u equals sine, because then the derivative would be cosine. And we say, oh, well, u du. So this becomes integral 0 to 1, because sine of 0 is 0. Sine of pi halves is 1. And then we have u du. Okay, so that's 1/2 u squared evaluated from 0 to 1. And that would be 1/2. Nice. All right, now the last integral, well, that one's not too bad. We can just straightforward 1/4 rho to the 4th, add 1 to the power, divide by the power from 0 to 2. And plug in 0, you get 0. Plug in 2. 2 to the 4th is 16. 16 times the 4th is 4. So this is 4. So we end up with 2 pi times 1/2 times 4, or 4 pi. And we're done with number 4. So, after that long diversion, on to number 5. A thin metal sheet is covering the region described by the sphere. X squared plus y squared plus z squared equals 9 in the first octant. Its density is 4z. Find the mass of this thin sheet. Okay, now, what do we have? Well, we don't have a whole sphere. We have a piece of a sphere. In particular, we have 1/8 of the sphere. And so we can do a really quick sketch. I don't know if we need to, but okay. So we have our x, y, z, and x squared plus y squared plus z squared equals 9. That says it's a sphere of radius 3. But we're only taking the part where we're in the first octant. So x, y, and z are all positive. So it's just this piece of the sphere here. All right. So there we go. So there's our region. And, well, I shouldn't say our region, our surface. Yes, it's really a surface, right? And now, what are we asked? Well, we're after our mass. Now, how do you find mass? Well, that's an application of integration. The way we find mass is we integrate density. It's always the same thing. So, we say, suppose we call this our surface G, then our mass is the integral over G of our density times dSA. Now, what's going on here? dSA means we're taking our surface and we're cutting up into little tiny pieces. So this is a little piece of G. That's it. That's what dSA means. It's a little piece of G. And so if you take a little bit of G times the density, well, that's the mass of that little piece. And then we add them all up. Now we're using two integral signs because there's a two-dimensional object. All right. Now, at this point, we're like, cool. How do we do it? Well, here's the idea. The thing is, it's a surface. We really are comfortable for doing two-dimensional integrals working in the plane. So we want to push this integral, which is a surface, push it down into that plane. That's the goal. It's a worthy goal. So we're going to do that. And so how do we get that done? Well, imagine, if you will, that we're looking straight down the z-axis. So we're way up high. We look down the z-axis. And as we look down the z-axis, so if we look from above, now if we look straight from above in this orientation, what would you see? Well, you see the sphere really turns into a quarter of a circle. Now, if we fix the orientation, so in other words, turn it 90 degrees, so what we have is that our region R in the plane is a quarter circle. So our goal is to say, hey, we're not going to do a surface integral. We're going to push and do an integral over a region in the plane. But what we have to do is figure out, well, how do we pull that off? Well, okay, so that's a great story. And here we go. Because G is over R, so G is over the region R, then this is going to become the integral over the region R of our density function. Now, let's be careful here. When we're in R, we want our density to be only in terms of x and y. Well, notice our density function is 4z. Can we put 4z there? No, we cannot. Why not? Well, because that's not an x or a y. So you say, okay, so what can we put? Well, what we can put is what z is. So notice we have that z squared is equal to 9 minus x squared minus y squared. So z is the square root of 9 minus x squared minus y squared. So 4 square root 9 minus x squared minus y squared. Okay, so that's this part. That's your density. Now we have to do this dSA part. Now here, that's going to be a whole computation. Let's come down here and run this computation. So this is our function. This is our f of xy. And what you have is that dSA is the square root 1 plus fx squared plus fy squared times dA. So we need to figure out what this is, and fingers crossed, it's something simple enough that we can actually figure out the integral. All right, so this, in our case, will be the square root of 1 plus. Now, if we take the derivative with respect to x, we're going to get 1/2 9 minus x squared minus y squared to the minus 1/2 times the derivative of the inside, which is minus 2x squared, plus, same thing, f sub y, 1/2 9 minus x squared minus y squared to the minus 1/2 times minus 2y squared. All right. Now, if this makes you nervous, it's okay. That's a very natural feeling at this point. But we're going to go for it. We have faith that our instructors still have a little bit of love. This is making us question that, but we still have a faith. And I say, okay, I believe you. I'm going to follow you. So the 2's cancel. All right, good. That helps restore a little bit of faith. And what do we have here? Well, okay, that's the square root of 1 plus. Now, what's left upstairs is an x. When you square the negative, that goes away, so you can write it as x squared. Now here, when we square this, it'll be to the negative 1 power. Right, negative 1/2 times 2 is negative 1. So that's like 9 minus x squared minus y squared. Okay, what's going to happen here? Well, same thing. The negative goes away. Y will be squared. And then we're going to get 9 minus x squared minus y squared. All right. Well, that's more promising. Okay, so this becomes the square root. Put it all together. Get a common denominator of 9 minus x squared minus y squared. So the 1 becomes 9 minus x squared minus y squared over 9 minus x squared minus y squared. And then, so this is the 1 plus x squared plus the y squared. Okay, so we had our 1 plus x squared plus y squared terms, right? Now, what do you see? Wow. More cancellation. Nice. Okay, and so what do you have? Upstairs you have square root of 9, which is 3, over square root 9 minus x squared minus y squared. Now, one thing I forgot to keep writing is all these dA terms, so we'll go ahead and add that in. And there we go. Okay, so that is that. Yeah, there we go. They're both together. So times by 3 over square root 9 minus x squared minus y squared dA. All right. Now, we finally feel the love. What's happening? The really terrible parts are canceling. So we end up with 4 times 3, which is 12. And the 12 you can pull out. So the 12 integral over your region dA. But what happens when you integrate 1 over a region? It's the area. Okay, so this is 12 times the area of R. Now, what is R? Well, that is 1/4, because it's a quarter circle of a circle, which has area pi times 3 squared. Now, 12 times a quarter is 3. 3 squared is 9, so 3 times 3 squared gets us to 27. So 27 pi. Whew! So at the end of the day, the actual integral turned out to be really, really easy, but the setup, that's where you put in the work. That's not too surprising. That actually happens a lot. It's the setting things up. That's the hard part. Never underestimate the value and importance of setting things up. Why am I waxing philosophical? I don't know. Let's go and do number 6. All right. Find the image of the region R enclosed by xy equals 1, xy equals 9, y equals x, and y equals 4x. And we're having that x is positive, y is positive. Under the transformation, x equals u over v, y equals u times v, and u and v are also positive. So, okay, everything's positive. Good to know. Good to know. So, all right, well, let's see if we can't think about what's going on here. Okay, so let's first off sketch what R looks like. So we're here in the x, y plane. And, all right, now xy equals 1. That's like y equals 1 over x. So that's something like y equals 1 over x. And we'll make it xy equals 1. Xy equals 9 is the same as y equals 9 over x. So it's similar to xy equals 1. It's a little bit bigger. So, okay, so it's, we'll say it looks something like this. So here's xy equals 9. And what else do we have? We have y equals x. And, okay, so that's this part right here. Y equals x. And finally, we have our last piece here, which is y equals 4x. So that's a little bit steeper. So this is y equals 4x. And now we say, if you put all of those together, then yeah, there's a little tiny piece. So this here, that's our region. Okay, now we don't necessarily need to know that. All we really need to know is what's bounding it. And okay, so we see that it's these curves. So the question is, what does this become in terms of u and v? So what we're going to do is look at every single bounding curve and say, let's rewrite that in terms of u and v. Now, they made it really easy for us because what have they done? They told us what x and y are in terms of u and v. Because there's two choices. You say, what is u and v in terms of x and y? What is x and y in terms of u and v? Because they told us x and y in terms of u and v, we just go through one by one and talk about what our bounding curves become. So, well, xy equals 1. We're going to replace x by u over v. So this becomes u over v. Y is u times v, and equals 1. Well, we can cancel the v's. So this becomes u squared equals 1. We'll take the square root. U is plus or minus 1, but u is positive. So we say, so that says u is 1. All right. Now, we're going to do this for all the bounding curves. So the u equals 1. And how about xy equals 9? Again, everywhere you see an x, put a u over v.
Everywhere you see a y, put a u times v. And where you see a 9, you put a 9. Again, the v's cancel, u's multiply. U squared equals 9. Take a square root. We only need the positive one. U equals 3. All right. Well, let's do y equals x. Okay, so y equals x. Everywhere we see a y, put in u times v. Everywhere you see an x, put a u over v. Well, we can multiply by v, divide by u. What does that tell us? Well, it tells us that v squared equals 1, or v equals 1. All right, and then finally, we have y equals 4x. Okay, everywhere you see a y, put u times v. Everywhere you see an x, put a u over v, and the 4 is the 4. Multiply by v, divide by u. You get v squared equals 4. So v equals plus or minus, but of course we don't need the plus. V equals 2. All right, so what does this tell us our region looks like? Well, in terms of u and v, so if we were in the u-v plane, we have u equals 1, and then we have u equals 3, and then we have v equals 1, and then we get v equals 2. And so there we go. There is our new region. I'll call it new region with a hat. A hat is just a way of saying, hey, it's kind of related, but it's not exactly the same. Right? It's a different region, or it's a different plane, but, it's our new region. Probably should have chosen S. In retrospect, S would have made a better choice. But okay, so what's the image? Well, the picture's good, and I think that would get full points, but they probably want us to describe it in terms of bounds. And so our image here will say that u goes from 1 up to 3, and we'll say that v goes from 1 up to 2. So there's the image. Nice. That leaves us with part B. Compute the integral over our region R of this function using the transformation in A. Okay, so the good news is we've done one of the three things. So every integral has three parts. There's the function, there's the region, there's the breaking things up. Now, we have the region. Let's talk about the breaking things up. So we're going to need the Jacobian. All right, so this is a change of variable problems, Jacobian. Whenever you see change of variables, Jacobian needs to be in your back pocket because it's going to come up. Now, in our case, where we have x and y as functions of u and v, what do we do? Well, we're going to compute the Jacobian. And so we're going to take the determinant of x sub u, x sub v, y sub u, y sub v. Now, if you're nervous about, did I remember to put the columns right? Did I maybe move stuff around? Or maybe I put xu, xv, yu, yv. Don't worry. The Jacobian is all forgiving. And so essentially, it's really hard to mess it up. The part that matters is make sure you have your partial derivatives in some sort of like logical systematic way, and take your partial derivatives, compute the determinant, and don't forget to take the absolute value, and we'll get to that in a minute. All right, so for us, what do we have? So this is going to be derivative of x with respect to u is 1 over v. Derivative of x with respect to v is minus u over v squared. Right? Derivative of 1 over v, that's like v to the minus 1 power. Derivative of y with respect to u is v. Derivative of y with respect to v is u. So 1 over v times u becomes u over v. And then we're going to subtract minus u over v squared times v. well, we can cancel a v, and that becomes minus u over v. And u over v minus minus u over v becomes 2u over v. Now, what is this telling us? First off, we checked, we need to take an absolute value. We are good. Nice! Well, okay, so what is this telling us? It tells us the following. This tells us that our dx dy, which is what we're currently calling dA, this piece right here, is equal to 2u over v du dv. All right, so that's going to be important. So you have to keep track, because if you don't have that, you're liable to be like, whoops, I forgot something. And if you forget something, trouble. Okay, all right, now we're ready to go. So here we go. Let's go ahead and strap in and find out what's going to happen. We have our integral over our region of 3 square root xy plus square root y over x dA is equal to our integral over our new region, which I threw a hat on, of, now we have to update our function. Okay, so xy. Now the good news is we just multiply these together. What happens when you multiply x times y? Well, we can do this computation here. X times y, we've already done it. It's u over v times u times v, which ends up being u squared. So the square root of that is u. So square root of xy, u. What about y over x? Okay, do the same kind of thing. Y over x. Well, y is u times v, and then divide by x is multiplied by the reciprocal, v over u. The u's cancel, so that's v squared. Okay, so the square root of y over x is v. Then you have 2u over v, du dv, or dv du. All right, we'll say du dv. All right. Now, it doesn't really matter because our region is a rectangle. All right, well, the good news is this is something we can actually integrate. Nice. Oh my gosh, this is good stuff. Okay, all right. Okay, all right. Let's be careful here. We want to make sure we caught everything, so I'm just double checking that no surprises, and we don't want any surprises. Those are never fun. Okay, yeah, everything looks good. All right, so we really should have been ready to throw in our bounds. So let's go ahead and throw those bounds in. Okay, so this is integral, and here we'll multiply in, that's 6u squared. Well, I know how to say 6u squared over v plus, and then 2u, all right, because the v's cancel, du dv, and we are going to go from, u goes 1 to 3, and v goes 1 to 2. Okay, so 1 to 2 of, when we integrate with respect to u, well, integral of 6u squared will be u cubed, you divide by 3, so you get 2u cubed, divide by v, v is the constant at this stage, plus u squared. And we evaluate from 1 to 3, dv. All right, when we plug stuff in, okay, plug in 3. So this becomes integral 1 to 2. 2 times 3 is 8. Sorry. I know how to math. 2 times 3 is 6, but really we should say this is 3 cubed. Oh my goodness. That's a huge number. Yeah, it is, but if it's a number, it's a number. So that's 54 over v, but then you're going to subtract 2 over v. So that gets you to 52 over v. So 52 over v, all right, And then when we plug in 3, 9 minus 1, that's 8. So 52 over v plus 8 dv, which becomes 52 log of v plus 8v. Evaluate 1 to 2. Now, when you plug in 2, you get 52 log of 2, and then you get plus 16. But we're also going to plug in 1. Log of 1 is 0 and 8. So it's 16 minus 8, which is plus 8. So 52 log 2 plus 8. I was running out of space, so I squeezed it all in. Oh, whew, that one's a workout. Well, these change of variable ones can definitely be a workout, but it's good that we made it through. We got to the end. That deserves a pen drop. And all right, I hope you're studying. Keep it up. Do great things. I know that some of these problems can look intimidating and some can look pretty straightforward. Be careful. It can be deceptive. Practice, practice, practice. The more you practice, the better you'll get, and it's all going to become second nature. You're going to do great. All right. Good luck.